All right. Is that font okay? Too big? Too small? It's fine. We can read it. All right. Because I'm on a different laptop here. I'm experimenting. Yeah. This is a Retina display MacBook Pro, so I'm getting rid of my MacBook Air.
Oh, that's the one you were saying?
Yeah.
I had a brand.
So if you're interested, it's a nice laptop. Pretty good deal. What was I talking about? Oh, well, the font size is good. Okay. So last time, see, we met on Tuesday, correct? Where did we leave off? The last thing, if I remember, we were implementing let star. Yeah, so we had a pre-process scope. Okay, yeah, this is what we did. So we wrote this function called pre-process scope, and pre-process scope took something in that looked like sample scope. So something that looked like this, which is an environment with two variables defined in it, right? An A5 and a BA, for example. All right, and then what it did, and we'll just run it real quick, is it created a list with two environment lists in it. So this guy is a scope in and of itself, correct? So here's a list with an A whose value is a lit expression 5. And then this guy is a list containing a B whose value is a lit expression or a var expression A. Why did we need to convert these to this one being a lit expression and this one being a var expression? Because we're going down a path where if we want to be able to, with a let star, if we want to be able to define B in terms of A, like we're doing in this case, we need to add this scope to our environment first. Then we need to resolve A. But what does it mean to resolve A? Resolve A means apply expression, correct? Given the environment. So in order to call apply expression on this, apply expression works on Basel code. So I needed then to convert something that looks like this in Simon into its Basel code equivalent here, which is B is equal to a value, and that value is an expression, and that expression is a var expression containing the symbol A. Similarly, A has a value, and its value is a lit expression whose value is the literal 5. That make sense? So then what we can do is we can call apply expression on this. I mean, right there, that is Basel code, is it not? That's an expression in Basel code that will boil down to a 5. This guy right here is also an expression in Basel code that will boil down to the value of A when resolved in the current environment. That makes sense? So for a let star to work, in this particular case, we need to make sure that we get this variable added to our current environment before we try to resolve this variable. That make sense? Okay, so we're going to try to do it kind of on a small scale thing here, and then we'll integrate it into our actual language. So right now we have this thing called pre-process scope, which just goes through and replaces all the values with the Basel code. Everybody, that makes sense to everybody? Okay. Well, now we need to evaluate this guy through apply expression, which means I need to add a scope for each of these. So we're going to start off with the empty environment. So we're gonna evaluate this on. We'll start off with our empty environment, which we have defined higher up here, wherever it is, right here. So we're going to call Apply expression, does he already know about a let? Here's apply expression. Okay, here's a Var Def Expression. And, okay, this is what we were doing, our up thing. Okay, so we need to add things to our environment one variable at a time in order, because that's how a let star works. A let star would not allow us to do something like this. It would not let us do this. We couldn't say A is equal to B and B is equal to 5. It has to be in the right order. We could say B is equal to 5, then A is equal to B if we turned them. But the way this is working is we are adding this variable as its own miniature scope to the current environment, and then applying this guy in that new environment. Does that make sense? Okay, so we need to be able to apply expression on all of the expressions inside of a preprocessed scope. That is, if my scope looks like this, I need to be able to apply expression on that entire thing. How would I do that? That is, I want to apply expression on this guy, and then I want to apply expression on this guy, with the understanding that when I apply expression on this guy, I need to apply it with the environment that was produced as a result of applying expression on this guy. So let's start with a baby step. How do I apply expression on just this first part? That is, I want to be left with a I want to take something that looks like this, looks like what I have highlighted there, and I want to boil down to an environment that has A in it with its corresponding value. So let's call this guy do we want to do it as a separate I want to take it as a super baby step. So define apply scope just for right now. An apply scope will be a lambda that takes in a scope as a parameter as well as an environment. Okay? So ultimately this is going to wrap into our add scope up above. So apply scope is going to take in our current environment and a new scope. And what are we going to do? Well, we need to process that scope. And what does it mean if a scope looks like this? So we could even call this a one scope, if you will. In fact, maybe that's even the better way of calling it, a one scope. So a scope defining a single variable. If that guy looks like this, we ultimately want to add this scope to this environment, but before we add it, we need to resolve the Basel code in here. So how do we resolve just this part of that guy? How do I resolve Basel code? How do I apply that Basel code? I do it with my apply expression. That make sense? So I'm going to say apply exp, I think that's the name of it, right? expr. Passing it my expression. If my input looks just like this, if that's my input, what I have highlighted there, how do I get just the expression part of that? Car the cooter? Car the cooter gets me that list containing the lit expression and the 5. So just to kind of show you where we're going with this, let me cut this real quick. If I say apply expr, passing it let me just type it. Passing it a lit.exp and 5, as well as the empty env, I get a 5. Okay, so if I call apply expression, passing it the Basel code for a lit expression, along with the starting point for the environment, I get a 5. That make sense? Now, what would happen if then I added to my current scope that 5? How does add scope work? Add scope, and I'm actually going to get rid of this add scope list, because I think we saw last time the weakness of it. Well, I'll leave it for now, but it has a weakness. So right now we want to add scope, we're going to take in a scope, where a scope is a variable environment. It's a list of 2 lists, right? It's a list of 2 lists where each 2 list has a variable name and its value. So it's a list that kind of looks like this. But all these Basel codes should be replaced by their apply expression version. So in this case, I need to pre-process this. So I turn this lit expression into a 5 before I add it to my scope. So if I say define curry in V to be add scope, is it all one word or like a hyphen or something? Add dash scope takes a scope in an environment. Add dash scope takes the scope, and what's the scope going to be? The scope is going to be whatever apply expression returns for that inside of a list So I'll build a list with A, we'll just hard code the stuff in there for now, along with whatever's returned for apply expression, all that stuff. Okay, so I'm adding that scope. So that is a list containing, actually it's going to be a list containing a list. Because ultimately what I'm producing here is something that'll look like A5. That is a single scope. That's a variable environment containing exactly one variable. So a variable environment itself is a list. Each variable inside that list is a list that has two elements in it, a variable name and a value. Okay, where I intend for our let star, I intend to pass it a bunch of scopes that only have one variable in it. So ultimately, I want to get this as my new scope. That is an environment with a single variable defined, whose variable name in this case is A, because that's what I'm building here, an A, but whose value is the result of applying expression on the lit expression 5. That make sense? Okay. So I'm going to initially, and I'll show you a couple things here. I'm going to set curry env equal to the empty env. We'll start off as the empty environment. Then we're going to change the value of curry env. Set bang. Set bang lets us change the value of a variable. We're not often going to use this. This is more just general knowledge stuff, because usually we're changing variables inside of recursion within a function. But this is how we do it at the high level. So I'll start off curry in v equal to the empty environment. Then I'm going to change the value of curry in v to be whatever add scope returns, passing it a preprocessed scope, that guy right there, along with curry in v. So I'll change curry in v in terms of itself. And then I'll just print out curry in v. All right, so this first line will just keep printing out this crap up here that we're going to use in a second. But then I'm going to define the empty environment. Then I'm going to extend that empty environment with a single variable scope that's been pre-processed, because I hard-coded in the pre-processed result here, so that we'll actually see it hold A5, not A lit expression 5. So there's our environment containing a single scope, and that scope contains a single variable whose value is 5. That make sense? Okay, so if I'm given this sample scope, something that looks like this up here, what I need to do is I need to walk through this one variable at a time. And for each variable, the first thing I need to do is I need to call preprocess scope to expand that, what I have highlighted there, into this. So I've expanded it so that all of the values are now in the form of Basel code. That makes sense? So now I've just expanded the whole thing. I've given myself a bigger list with a bunch of Basel code now. So now I need to build up an environment, one variable at a time, where I add this variable to my environment first, which will then allow me to add this variable to my environment. Make sense? I need to do them in the correct order, and I need to produce a new environment each time, which is like what we're doing right here. So I have my current environment, which started off as the empty environment, and I'm expanding that empty environment to be a new version of current environment. That is the environment that results in taking my original current environment, adding a new scope to it. What scope am I adding? I'm adding the scope that only defines A as 5, which then would allow me to add an additional scope of B being able to resolve the value of A. And I'll show you that. So what I'm going to do here is I'm going to steal this line, paste it in here again. So we're going to add another scope, but this one's going to be, the scope we're adding is variable B is equal to the var expression A. Notice it matches what I'm doing here. I just created that. Okay? So that's my second thing. And I'm going to do that in terms of curry env. So curry env here is the curry env that was returned from this guy, which is the one that has the resolved version of my variable A in it, which should then allow me to pre-process, apply expression right here to get the value of A, resolve A in curry env. Except this needs to be cur env, and this should also be curry env. I started off as the empty environment. So curry env is the empty environment. Then I add my first scope, changing the value of curry env to be whatever is returned from add scope, passing it my new mini scope, the environment containing one variable and a resolved value. And how am I resolving the value? I'm resolving it by calling apply expression, giving it the Basel code, and giving it whatever the current environment is, which this first time through will be the empty environment. Okay, and I'm adding that scope to whatever the current environment currently is, which will produce a brand new version of current to env that looks like this. Then I'm going to do it again. Next time, I'm going to overwrite cur_env with whatever is returned by add scope. Add scope always returns an environment. And what do I pass into add scope? I'm passing it a mini scope, that is a list containing a single to list, where the variable name is b, and the value is whatever's returned on apply expression, passing it the var expression a, and the current env. Notice that the current env does indeed have a defined in it. And the environment I'm expanding is cur_env. So after I run these two lines and I print out cur_env, I should be left with an environment that has two scopes in it. The most local scope will be a scope that has b is equal to 5, because that's the value of a. Does that make sense? The second environment will be a variable a that's equal to 5, because 5 was a literal. Does that make sense? But I could not have resolved b is equal to a unless I already had a in the environment. So I'll run this. Oh, everybody relax. Is it that? Is that how it works? There we go. User error. Our code was fine. That's why we write code in Simon, not Bazel code. We have to. We see how easy it is to mess up our Bazel code when I just hard code it in there. Okay, so does this make sense? So right here, this is the step-by-step version of starting from the empty environment and adding a scope, then adding another scope. So I need to automate that. Okay? I need to automate that by pre-processing the environment that came to us from a let star, where that environment might look like this. So here's a sample scope from a let star. So we already have this pre-process thing producing this for us, which is exactly what we want it to look like. But now, step 2, that we've proven will work, because we just did it manually by hard coding crap, is we need to add this scope first, producing a new environment, and then add this scope second, producing a new environment, and then add any additional ones that we have. Okay, so I need to now process this environment one sub-environment at a time, one sub-scope at a time. So pre-process scope does this. It takes in our scope, it maps wrapper to that scope, where wrapper is this guy that called parse Simon on the Bazel code. So we're going to actually write a helper function here, then we'll end up integrating the two together. So we'll do define process let star Bazel, I guess, ish, KK, thanks. And this guy is going to take as a parameter list of scopes. List of Bazel scopes. Lobs. Huh? List of BS. That's what it takes. It takes a list of BS. All right? So the input to this guy will look like this. That make sense? So its input will be the output of pre-process scope. So we'll call process let star Bazel, and I'm pretty sure I can name it let star like that. Well, I guess we'll find out, but I'm about 99.5% positive that works fine. So it's going to take in a list of Bazel scopes, and what I want to do is I want to process those scopes one at a time. So it's also going to take in an initial environment, a starting point, so whatever the current environment is. And I'm going to create a cond. Cond is going to ask that standard question, null lobs, turn the empty string. Otherwise, if it's not null, the car of that guy must be a what? Must be a one scope. It must be, the car of that guy looks like that. That is a one scope, but that one scope has not been applied yet. That is, we haven't done this to it. We need to build that guy out of it. Which is a new scope. All right? So, we're ultimately going to do all that stuff right here. So else, add a scope. What scope am I adding? I'm going to create a list that contains a single list. The variable in that list needs to be whatever variable I extract. So I'm going to take the car of this guy. So the car of this guy is going to look like that. I'll just copy this here real quick. So I have something that looks like that. And I need to create a brand new list that contains a list whose first value is that. If this guy is the car, so the car of lobs would produce something like this. And I need to create a list containing a single list whose first element is this A. How do I get at that A? The car of the car? So, car of the car, lobs. That's my variable name. Because I'm essentially building a scope here. That is, I'm building, here's my variable name, and then I need its value. And the value is going to be the result of apply expression on this part, the Basel code. So, car of lobs is this. How do I get to that piece? The car of lobs gives me this whole thing. The cdr of that gets me the list containing this, and then the car of that. The CADR, cdar. So I'll take the car, which gives me this. Then I'll take the cdr, which gives me the list containing this. Then I'll take the car of that, which gives me that Basel code. So I'll call apply expression on the cdr of lobs, passing it whatever the current environment is, which is the environment I'm passing around inside of process let Basel, process let star Basel. That makes sense? So I'm going to take whatever is returned by this, which is a brand new one scope that has been passed, whose value has been sent to apply expression. And I'm going to add that scope to whatever the current environment is, E and V. That makes sense? Now, what am I going to do with that environment? What I have highlighted here will produce an environment. That's what add scope does. Add scope is a constructor for building environments. Sure, I'm applying Basel code in there and stuff like that, but the means to an end is that I did the whole apply expression to get the value for the variable that I'm adding to my current environment. So at the end of the day, after all this crazy code, what's going to come out of this is a brand new environment. That's what add scope does for us. Okay? And what do I want to do with that environment? Well, I might have some more lobs. I might have some more Basel scopes. Therefore, I need to call process let star Basel again, passing it the rest of lobs, as well as what? This is my environment. Now, when all is said and done, and we finally run out of lobs, I'm not returning the empty list. I'm ultimately going to return my final environment. That is this guy. Does that make sense? So I'll just return E and V there. And what am I doing here? I'm going to call process let star Basil, passing it two pieces of information. The first one is the cdr of lobs, so the rest of that list. And the second one is the environment produced by processing the car of lobs. That make sense? So now what I should be able to do is I should be able to call process let star dash Basil on preprocessed scope, sample scope, along with the empty env. And it should ultimately boil down to what we did manually before. Okay, so I'm going to call that function we just wrote, passing it as input this, along with a starting environment that has nothing in it. And it should produce for me my updated environment that has two scopes processed in the right order. That make sense? Okay, so my guess is 6 of you followed that. Who are the 6? Let's see if I guessed the right the right number of hands. Dane? What the heck? I got that. Now, the reason why I have not been giving you these things as homework is that was fairly complex what we just did. And the reason was you had to break it down into little tiny baby steps. But what's important for us to understand from a programming language theory perspective, I mean, that code wasn't hard, just the steps to get to it, we had to think through a relatively complex problem, right? That's going to be kind of a reach for some of us at this point. But, I mean, that's not important. What's important is we understand how that let star can work. We made it work by taking an environment. So how do lets work? Let's create a new environment as well as a body for that environment to operate on. So at the end of the day, in order for a let star to work, we need to be able to give a value to A that is based on resolving the value of an expression. And we can't resolve the value of this expression until we have the value of, this one. Forget about this for right now. We haven't even written that into our code yet. We can't resolve the value of A until we have the value of A. That make sense? So the big difference between a let and a let star is that one thing. That lets would never allow us to do this because lets are easy to write, relatively speaking. We wrote a let 2 classes ago, correct? I mean, this stuff is becoming, hopefully what we see is that what we're accomplishing is drastically more complex, yet the level of difficulty from our understanding perspective has stayed about the same. Things that seemed hard for us to understand at the beginning of the semester now seem trivial, and writing the code for a let seems about as difficult as stuff was at the beginning of the semester. I mean, all of it is a little bit confusing because our minds aren't working this way. You know, we don't think like a language builder. We think like language users. Kind of make sense? So, in order to go from a let to a let star, we had to allow for this behavior, defining a variable in terms of a value that was set previously inside the let. And the only way for us to accomplish that is to pre-process that let by adding each individual variable and its corresponding value to a running environment one at a time. So that at the point when we go to get the value of A here, it's already in our environment. That makes sense? And we accomplished all of that through these two functions. And we could have done it in one scary function. But the first one went through and essentially did parse Simon on a scope. So we could easily call this guy parse scope. That makes sense? Turn a scope into its Basel scope equivalent. Because isn't that what parse Simon does? Doesn't parse Simon take in something that looks like relatively simple code, something like that, and turns it into something that is a little bit less simple? That's what it does. So by our definition, we might call this guy parse scope. And then what should this guy do? Process let star Basel. Well, we might call this using our vocabulary, apply scope. That makes sense? Just like apply expression. Apply scope takes a list of scopes. List of Basel scopes is how I named it. In the starting environment, and it produces a brand new scope, which has everything resolved. I didn't change any of the logic. I just updated the names to kind of be consistent with what we did with expressions. Simon, when we write Simon code, we're writing a legal Simon expression. How do we execute it? We call apply expression, passing it Basel code. Because parse Simon turns Simon syntax into Basel syntax. Apply expression takes Basel syntax and executes it within an environment. What does parse scope do? It takes a scope written in Simon syntax, converts it to an equivalent scope in Basel syntax, and then apply scope takes in a list of Basel scopes and the environment we're adding them to, and adds them one at a time from left to right. Make sense? So the important thing, I don't expect you, I don't expect most of you to be able to write that, but I want you to be able to follow it. Okay, so you're with me? All right, so now that we have these two guys, where the input to parse scope looks like this, and what is that? It looks like the environment part of a let star Simon expression. That makes sense? So if we're looking at a Simon expression whose car is let star, so this guy up here. So we would go and look at, oh here, let me ask, let's see how well you understand this. If I have something like this, what I have highlighted there, what do I need to do to that code? What's the next step in terms of executing this Simon program? So if we're making a recipe here, we're making our lasagna, What do I need? If that's my input, what do I need to do to it? Go higher up. Look at exactly what I have highlighted. That's exactly what my input looks like right now. What I have highlighted. What do I have to do to that before I could do anything else? Convert to Basel code. How do I do that? Oh. Parse Simon. So if I'm looking at Simon code, what do I need to do? I need to turn it into Basel code. How do I do that? Parse Simon. Now I have Basel code. Great. So let's do this one little step at a time. What's this?
Said we could have just named it regular names.
They would be less memorable.
Or more memorable.
I doubt it. I doubt it. So I'm going to call parse Simon on SE7. So here's my SE7. That's that let expression, the thing I just had highlighted. So when I call parse Simon on that, we're going to still have this line show up for right now, but there will be a second line that has our output. What is it? Capital S, no dash? That? Yep. So this guy is going to boil down to, we still need to write parse Simon. We're not done with it yet because it thinks it's, oh no, we're good. Var Def Expression. So this is a variable definition expression in Basel code. And that guy contains a list who has two elements. The first element of it is what? What is that guy that I have highlighted?
Scope.
It's a scope. What do I need to do with a scope that looks like that?
Apply scope.
I can only apply scopes that look like Basel code. I need to parse that scope. You with me now? All right, so I'm going to move this code up there. So I'm just going to move these two functions as is higher up so I can call it from above. Whoop. Okay, so I'm going to go all the way up to parse Simon. I'll actually put these right before parse Simon just for the sake of whatever. So when I'm creating something that is a Var Def expression, right here is my catter of that guy, correct? The catter of my expression is the scope I want to pass to parse scope. So I want to take this guy right here, and I want to call parse scope on him. That makes sense? I'm inside parse Simon. Right now, a Var Def expression boils down to an unparsed scope. I need to make sure that that scope gets parsed into a Basel scope. So what I have highlighted right there isn't what it should look like. It should look like list A, lit expression 5, list B, var expression A. That make sense? I need this whole thing to be Basel complete. That's a fun word to say, fun phrase. This needs to be Basel complete. That means that the entire thing needs to be in Basel syntax. Not just the expression part, but also the scopes. So if I run this again, by just making that one little change up here where I'm calling parse scope on that. Now notice that my scope here is what I expect it to be. Oh, let's show you this whole. Notice what my scope looks like now. That look like a Basel scope? Well, I need to, sorry. Now does it look like a Basel scope? So it's a list containing two lists. The first two lists, first element is A, the second element is the lit expression. The second two list, first element is B, second element is the var expression. Which all Basel code, right? So that's what parse Simon does. Parse Simon takes something in that starts off like this. So what I have highlighted there is the original Simon code. And this is the output of calling parse Simon on that code, which just says convert Simon syntax into Basel syntax. So it's a let star that translates into a var def expression. Here is the environment of that guy. Great. That's going to translate into this Basel scope. So this is the scope that governs that let star. So I'll turn it into that Basel scope. Finally, I have a math expression, which is the body of my var def expression. And here's that, my math expression. Make sense? So all we did there is turn simple, high-level Simon code into much less simple, lowish level Basel code. These two lines are equivalent, just in two different languages. Make sense? So now what we need to do is we need to go into apply expression and teach it how to properly apply a var def expression. And we do that by utilizing our apply scope function. So we'll come into apply expression. And here's our var def expression. Var def expression calls apply expression on a bunch of stuff, but we don't want that. We're calling it on this add scope thingy, but we really need it to work differently. So we're calling apply expression on the expression portion of this, which is this guy right here. At bucket 1, that's the list ref bucket 1. So that's the actual expression that I'm applying. But I need to apply it in a new environment. That is the environment returned by applying scope with the list of Basel scopes in the current environment. So right here where I call var def expression, when I apply this expression, I'm applying it to this expression in this environment. The environment that happens from adding a scope to my current environment. That was where our add scope list came from. So this is how I get at my scope portion. So the rest of this I'm actually going to get rid of here. And what I'm going to say is I'm going to say apply scope, passing it that guy, my scope, my list of Basel scopes, my lobs. That's my lobs right there, right? It's my list of Basel scopes in my var def expression, along with my current environment. That make sense? Yay, nay. Understand that we're actually only doing two very simple things. I know it seems like we're providing a doing brain surgery, and it doesn't seem to be going well. But trust me, this is going to work. We're only doing two little baby things. So right here, that is my list of basal scopes. That's what that will boil down to. Bucket 0 of this guy. That's my list of basal scopes. Right there. Right there. That's bucket 0 of that. Bucket 1 is my body of the let star, which is that guy. So here's my bucket 1. That's the expression that I need to apply. So I'm applying an expression. In this case, it's going to be a math expression. And I'm applying it inside of the scope created that gets returned by apply scope, giving it my list of basal scopes and whatever the current environment is. Okay? So, given all of that, I should be able to come down here, get rid of those things. I should be able to say, apply EXPR on the parse-Simon version of SE7 given the empty environment as a starting point. And this is SE7 right here. My empty environment has no variables. After I add these scopes, I should have A is 5, B is 5, A plus B is 10. So if this works, I should get a 10 printed out, because eventually, when I call apply expression right here on my Var Def expression, I'm going to be applying it on this math expression. Math expression is going to come in. I'm going to do my math expression, which calls apply math expression, which is right here. And if it's a plus, I'm going to add the two together. And there's my 10. And now we can actually make this even cooler, prove it works on bigger things. So we're going to say C is times BA. And I can do this now. This seems like it's way more complex than what I did before. But it's okay, because I'm calling parse scope on that. That will turn that value into something I can use. What's B times A? B is 5, A is 5, that's 25 for C. And then I can say A plus C, which should be 30. Oh, everybody relax. Hold on. Everybody really relax. Oh. There we go. Again, user error. See how that works? So we started off by writing this to just work for lit and var expressions, but accidentally made it work for any sort of expression. Literally any expression. Anything that Simon supports, I can now use in here to set values for my variables. I could put a let expression in here. I could set C equal to the result of a let expression. And then hope that somehow makes sense. Our language isn't mature enough to have that make sense yet. But I could do it because it's a valid expression. Similarly, out here I can say plus B. Now I get 35. Doesn't what I just wrote here look way more complex than what was there a second ago? Yet, my language works. Because I've broken it into little tiny pieces. And everything's done in terms of parsing and applying. Parsing is our equivalent of compiling. We turned Simon code into Bazel code. Once we have Bazel code, we have an interpreter called apply expression that knows how to execute Bazel code if you give it an initial environment. And see, we can even make this even cooler. Times R. So R is a variable that was never defined, correct? Right? I never defined R anywhere. Well, what I'm going to do is I'm going to add scope R2 to the empty environment. So I'm going to give myself a global variable called R that's equal to 2. So now I should get 70. That make sense? I provided it with starting points. Something to work on to begin with. Go ahead.
Did you have to do the add list or add scope, or could you have just said empty environment?
I could have hard coded in an environment. Yeah, I could have done this. I didn't have to use. Yeah, I could have done that.
For the sake of code.
Well, because I can't write this code. That's clearly that's the problem. Yeah. Oh, don't call that scope anymore either. Yay. So you got me all discombobulated. There we go. Oh my God. There. Okay, apply expression. That expression on this scope, which is a list containing a to list. Like that. See how bad I am at this? Let's see. I could write the hard parsing code and all that stuff. I can't write Bazel code from scratch. An environment is a list containing
Should just be R, not the.
that's what I had initially. Isn't that what an environment looks like? Oh, no, it's not. That's what the environment needs to look like. It's a list of scopes, where a scope is a list of to lists. So I'm going to go out on a limb and say my whole add scope thing was cleaner. That. That's better. That way we're clearly adding a scope, this guy, onto whatever our starting environment was. So we're adding some global variables. I can add a couple more global variables if I want. Q is 7. And then I can divide all that crap by Q. Make sense? So we got a pretty powerful language of numbers. Okay. Questions about any of this? What would the next step for our language be? So we made it work for let star. What's the difference between let star and let rec? Let rec is what? Yep. Let rec allows us to define variables in terms of themselves. What would we need to do to make this work for that? So right now we have it working for defining variables in terms of previous variables, previously defined variables. But let's say that we had something like this, SE7, and we said that B is equal to plus, actually we need to make sure we have at least a reasonable B is equal to lambda x Do we have an if expression already? What does our language support? Okay, we have an if. That's fine. We don't have such thing as a Boolean, but just to kind of give us a head start, because we're just going to discuss this. If equals x1 x, otherwise b of minus x1. So what if we wanted to support something like that? Huh? So while let rec, we can generically say it allows us to create variables in terms of themselves, what we're really saying is it allows us to create variables whose values are functions. Actually, let me ask you this. That's only a half-truth. Say b is equal to lambda x plus xa. Okay, so let's say this is my function. We're going to have a let star. Inside this let star, we're defining a variable named a setting equal to 5, a variable named b setting equal to a function, a lambda expression that takes a single parameter and returns whatever the parameter is plus this variable a. So this is a math expression. X is bound here. And ultimately we return, this is just another variable we don't actually use. In fact, let's just get rid of it because it's just going to throw a wrench in this example. And what we're going to do is we're going to take b and apply it to 7. I have a feeling that we did not write our lambda yet in apply expression. Yeah, we did not. So we have not written our lambda yet. So what we want to do next time, and then we'll talk about the final, is we want to finish this off by writing our lambda. Where's my parse assignment? We need to do our lambda as well as our app expression. We need to add those to apply expression to kind of complete our language. And what that would allow us to do is it would allow us to create a variable like this, where b is actually a function, and we can apply that function, this is a lambda expression, to an input, because this whole thing is an app expression, right? That's an app expression where the first expression is the lambda expression. The second expression is a literal expression. So if I applied b to 7, I would pass in 7 here. 7 plus a is 5. That should give me a 12. Make sense? So that would kind of complete our language in a very rudimentary sense. All right, so we'll come back on, actually, what time is this class over? 20 or 25? Oh, so we got time. We got time. We can write this. we got this. Okay, so we need to come into our apply expression. Yeah, the reason I got a false is because if I don't see any of this crap, I just bail and say it's false. So now we need to look at EQV car Basel is a lambda. If I'm looking at a lambda, lit var def math, let's just make sure we're going in the right order here. Lit var def. Oh, we didn't do an if either, did we? No if. Okay, well, we'll just go with we're going to do lambda next. Okay, so we have this. What? Okay, yep. So, if I'm looking at a lambda, what do I want to do? A lambda, let's actually, well, here, let me just take this whole thing out for a second. And we want to review what a lambda looks like. So that would be, let's just create a simple lambda. Define SE6 to be a lambda that takes in an x and boils down to x plus 5. Do something like that. And then what we want to do is we will call parse Simon on SE6 to see what a lambda looks like in Basel. So a lambda looks like this, lambda expression. So actually we need to ask if the car is lambda expression, not lambda. And then it takes in a list whose first element is the list x. And whose second element is the body of that lambda. I need to be able to take in as a parameter a value for x. Somebody's going to eventually call my lambda here. They're going to say something like this. If I come into SE6, here's my lambda, so I'm going to add to this. I'm going to say 10, like that. So now we have an app expression whose first element is a lambda and whose second element is a lit expression. And let me ask you this. Is there a such thing as an app expression whose first element is not a lambda? For example, here's some examples of app expressions. Plus 3, 8. That's an app expression, right? That is an expression followed by 0 or more expressions. In this case, we have 2 additional expressions, a lit expression and a lit expression. Does this guy start with a lambda?
No.
Trick question. Assuming. Go ahead. You were saying?
Plus probably has a method that starts with lambda.
Yeah. The plus is the name of a function, right?
Oh man.
Somewhere in here we have a lambda. We have somebody did this. Define plus to be a lambda, and that lambda takes in a value and another value, and we boil down to Well, it's going to be a little hard to define it in terms of itself, but the world just ended. But let's just assume it was the word plus. Okay? Somebody defined that built-in function as with a lambda, right? They had to define what addition was. That makes sense? So, this guy is a lambda. So an app expression always starts with a lambda. And then the next things, there are as many next things as there are parameters in the lambda. That make sense? So if I have a lambda that takes 2 inputs, like plus would be, I need to pass it 2 inputs, 3 and an 8. So my lambda is my plus. First parameter is a 3. Second parameter is an 8. It boils down to an 11. That makes sense? That's what an app expression looks like. So an app expression is always going to be apply lambda expression. We're going to have to write the ability to apply a lambda expression, just like we wrote the ability to apply a math expression. Apply a lambda expression in the environment that we currently have, given the parameters, the list of parameters that are coming in as input to this lambda. That makes sense? That's how an app expression will work. So an app expression cannot exist without a lambda expression. A lambda expression can exist without an app expression, but it can't be executed without an app expression. The app expression is what allows us to take a lambda and apply it to inputs. It's what allows us to actually call a function. A lambda is how we define a function, and an app expression is how we call a function. Make sense? All right, we'll talk about that more on Thursday as well as the final.